Hello, we are in Chapter 5, Integration. We are in 5.1, Approximating Area, and today we look at sigma notation, a fun and exciting way to express our Riemann sums. Let's take a look. Introduction to sigma notation. So this is sigma notation or summation notation. The idea is that you have a big Greek letter sigma, the capital sigma, and we write below it something like k equals 4 and above 7, and we have some expression in k. And this means I'm going to add together. I imagine the values of k go from 4 up to 7 by 1s, so 4, 5, 6, 7. And I add together all the results. So k equals 4, k equals 5, k equals 6, k equals 7. Do you see how the k gets substituted each time to create the expression? And then sigma for S for summation, we add them all together. The number on top is called our upper limit. The number on the bottom is our lower limit. And the thing I'm adding together is called the summand. So we used k before, but it really doesn't matter what variable I use. I could use I or j or n or gamma or whatever. The variable we use is often called a dummy variable because it doesn't really matter. And in this expression, I goes from 1 to 100 of I squared. 1 squared plus 2 squared plus 3 squared, on and on and on, up to 100 squared. Here's an example where we start at 0. Now, I'm always counting up by 1s, so this tells me that j will be 0, and then 1, and then 2, and then 3, and then 4, and then 5. So there's our expression for j goes from 0 to 5 of 2 to the j. This has 6 terms. One of the advantages of starting at 1, we don't always start with 1, but one of the advantages is that if you do start with 1, then the number on top is an indicator of how many terms you really have in your summation. 2 more examples. Let's say that I have a function defined. My function is x cubed plus 1. How do I figure out the summation as k goes from 1 to 4 of f of k? Well, let's just plug in various values of k. When k is 1, I get 1 cubed plus 1. When k is 2, 2 cubed plus 1. 3 cubed plus 1. 4 cubed plus 1. There it is. And for what it's worth, you could add all these things together, and it turns out that the answer for this is 104. How about this one on the bottom? Let's say f of x equals x squared. What does this summation become? One thing that's curious is that my upper limit is a variable n. That's okay. It just means we have a variable number of terms. So let's begin. K equals 1 looks like 1 plus 1/3 squared. And then when k is 2, 1 plus 2/3 squared. Plus 1 plus 3/3 squared plus 1 plus 4/3 squared plus on and on and on. And I'll stop eventually at n. 1 plus n over 3 squared. So I have n terms altogether, and the terms look like this. In these problems so far, I've been given a sigma notation, and I need to expand it out. Let's go the other way. Let's suppose I start with an expanded expression, and I want to condense it using sigma notation. This is actually the direction we more often go. So to begin, my k values will be 1, and then 2, 3, and 4, and I can see what I need to do to k in order to get the expression up above, in order to get the term that it corresponds to. It looks like I need to double it. So how about summation? K goes from 1, and every summand looks like 2k. And then I can see 100 is the last guy, so that tells me k equals, all I need is 50 up at top. Next problem. My values of k will go 1, 2, 3. What do I need to do to k? It looks like I'm adding 6 every time to get that denominator. So summation, k equals 1, and the summand looks like k plus 6. And I end at 20, so it looks like my top limit will be 14. How about this third one? If you need to pause it for a second and make your best guess, do that right now. Can you see what it'll be? Now the denominators go up by 3. 1 to 4, 4 to 7, 7 to 10, they're going up by 3. You'll get a hang of this. That's a good indication that I'm going to have a 3k in the denominator somehow. But if I do 3k, then I overshoot. It looks like I overshoot by 2 each time. So how about the summation k equals 1, and then in my denominator 3k minus 2. And then I can figure out what my upper limit has to be, 34. 3 times 34 is 102, and I'll subtract 2 to get the 100. All right, last problem. In sigma notation, k equals 1. Well, it looks like my numerators just go straight up, 1 through n. So I've got my variable on top, n there. And it's simply k over n squared. And the n appears in my sum end as well, and that's okay. That happens. Okay, so we've looked at summations. We've taken a summation and expanded it. We've taken an expanded form and condensed it into sigma notation. Let's do a couple Riemann sum examples, and our goal is to put the answer into sigma notation at the end. So here's our first example. Let's find the Riemann sum for the function f of x equals 3 minus 1/20 x squared on the interval from 2 to 10 using 24 right endpoint rectangles. So two things that are different from previous problems. One is it's a big number, 24. I don't want to have to write out 24 things. This is why sigma notation will be helpful. Another thing that's different is that if you look at the end of this function, some of my rectangles go below the x-axis. That's okay. I've been figuring out the areas as height times width and height times width. For the right side, my height will be a negative value. But that's okay, and in fact that's actually what I want, and we'll see why I want negative values a little bit later on in the course. So let's tackle this. We have to do 4 things. We have to find the rectangle widths. We have to find a formula for the right endpoint because we're using right endpoint rectangles. We're going to figure out f of the right endpoint, which is the height of the rectangles. Now that I have height, I can multiply height times width to get the area of the rectangles. And again, that's the height, and I'll put height in quotes because it could be that our height is actually a negative value. Let's do it. So number 1, let's find the rectangle width. Do you remember the formula for this? I will take the right endpoint minus the left endpoint and divide by the number of rectangles. And we find that every rectangle has width 1/3. Oh, check. Number 2, find the formula for the kth right endpoint. Let's just start listing off the grid points. It starts at 2, and the width is 1/3, so my grid points go 2, 2 plus 1/3, 2 plus 2/3, 2 plus 3/3, 2 plus 4/3, and so on. It's tempting to just simplify this to write it as 3, but don't do that. Keep writing your grid points with a pattern that clearly shows a progression. And so the right endpoint is going to be x bar sub k. Oh, incidentally, some books call this x star sub k. So you might see bars or you might see stars, but they kind of mean the same thing. So x bar sub 1, there's my right endpoint for the first rectangle. X bar sub 2, x bar sub 3, x bar sub 4. What is the formula for x bar sub k? Do you see it? The 4 matches with the 4, the 3 matches with the 3, the 2 matches with the 2, and in general, x bar sub k is 2 plus k over 3. There's my formula for the kth right endpoint. Check. Number 3, let's actually find f of x bar sub k. So I take my x bar and I plug it into x in my function. So here it is. This is the actual now height of the kth rectangle. Last step remains. Let's multiply height times width and add them all together. So I will use sigma notation. Sigma k equals 1. What's my upper limit? Well, it's the number of rectangles, because for every rectangle I will multiply height times width. So I have 24 rectangles. 24. And the height of the kth rectangle is all that stuff. 3 minus 1/20th, 2 plus k over 3 squared. And the width of the kth rectangle, well, actually, it's a constant. All the widths are the same. 1/3. And that is the answer. So in the homework problems, a lot of our problems end up being answers like this. Take a Riemann sum and express it using sigma notation. And this is good. I could do this for 24 rectangles. I could do this for 24,000 rectangles. The nice thing is, it gives me a formula that I actually could plug into a computer to find the Riemann sum. One more example. Find the Riemann sum for f of x equals 7 over x on the interval from 4 to 19 using 50 left endpoint rectangles. So we'll follow the same recipe as before to get our solution. So first, find the rectangle width. 19 minus 4 over 50 reduces to 3/10. So every rectangle has width 3/10. Now, find a formula for the kth left endpoint. Here are my grid points: 4, 4 plus 3/10, 4 plus 2 times 3/10, 4 plus 3 times 3/10. Do you see how we're just multiplying more and more of those rectangle widths? It's like I start at my left endpoint and I add a rectangle width, and I add another width, and I go 3 widths to the right, 4 widths to the right, and so on. So every grid point looks like my endpoint plus a certain number of multiples of the rectangle widths. Now, I want left endpoints in this problem. So my x bar sub k, my 4 is going to be x bar sub 1, and it'll move on from there. The formula for x bar sub k is a little trickier in this problem. Look at this. X bar sub 5 corresponds to an expression that has 4. X bar sub 4 has the expression where there's a 3. X bar sub 3 uses an expression with a 2. And in general, x bar sub k looks like 4 plus k minus 1 times 3/10. This often happens when we're using left endpoints. We get a k minus 1 factor in there somewhere. So, let me check that off. Third step, find f of that thing. So f of x bar sub k, let's take that whole expression and plug it in for x in my function. So there's my rectangle height. There's the height of the kth rectangle. Check. And as a last step, let's add them all together, and that's where we get our Riemann sum. K goes from 1 to 50, because I have 50 rectangles. This number on top is always the number of rectangles. The height, which is my f of x bar sub k, times the width. Let's take a look at the general form of the Riemann sum. In general, we have some function f that's defined over an interval from a to b. And we divide the interval into several subintervals. So on these subintervals, we will build the rectangles. And in each subinterval, I choose a sample point. Now, the sample points are often the right endpoints or the left endpoints, but they don't have to be. They could be somewhat randomly chosen. And to determine the height of the rectangle, I figure out the function value at the sample point. The function value at the sample point tells me the height of the rectangle. Take a sample point, find its function value, that's the height of the rectangle. Sample point, function value, that's the height of the rectangle. So there I have heights, and then for every rectangle I multiply the height of the rectangle times the width, which will be a constant. All the rectangles have the same width. And there it is. There is our sigma summation expression for the general Riemann sum. This is an impressive formula, and it's a useful formula. We will be using this formula a lot in the next few days, so it's good to memorize it, get to know it well. At some point when you're not thinking about calculus and you suddenly think about calculus, see if you can write this formula down without looking at your notes. So that is it for this lesson. Give these homework problems a try, ask me if you have questions, and show this formula to somebody and really impress them.